Where does MRI signal come from? It comes from hydrogen nuclei, which in the human body is mainly found in water and fat. We can think of these hydrogen nuclei as functioning like tiny bar magnets. So, hence the pictures. Before we extend this analogy further, I'd like to pause and reflect on how this is fundamentally different from all of the other imaging modalities in radiology. In CT and X-ray, we shoot high-energy photons, or X-rays, at a patient and see whether they get blocked or pass through the patient and hit a detector. In ultrasound, we use a transducer to send sound waves into a patient, which then reflect off of structures that have different acoustic impedances and come back to the ultrasound probe. Based on the amount of time it takes between when the ultrasound wave was generated and when that ultrasound wave gets received by the probe, we can infer how deep structures are in the human body and create ultrasound images. In nuclear medicine, we inject patients with radiopharmaceuticals that undergo radioactive decay and ultimately lead to the production of gamma rays, which we can then detect with gamma cameras. So MRI is totally different. We don't have to shoot X-rays at a patient. We don't have to use an ultrasound transducer to send sound waves into the patient. We don't have to inject them with radiopharmaceuticals that emit gamma rays. We just use the patient's own hydrogen nuclei and their water and fat to be able to generate signal. And the reason that we can do that is because these hydrogen nuclei function like little tiny bar magnets. They're magnetic. So how do we convert the patient's magnetism into an MRI image? So there's a relationship between magnetism and electricity. So if we can somehow take the patient's magnetism and convert it into electricity, send that into a computer, theoretically, we should be able to generate an image from that. So obviously it's a lot more complicated, but I wanted to start with a high-level overview. So let's begin with our first question. So go ahead and pause here and do your best to answer the question. I will go over the answer in a little bit. Okay, so where does MRI signal come from? It comes from hydrogen nuclei, which we said function like tiny bar magnets. And we can represent bar magnets as vectors with a magnitude and a direction. So if you've ever played with bar magnets, the ones that have like the North Pole and the South Pole, we're just going to arbitrarily say that the direction of the vector, it's towards the North Pole, okay? So if we're thinking about what these vectors are going to look like in the context of a patient, they're going to be oriented in random directions. When the patient is outside of the MRI scanner, the hydrogen nuclei and their water and fat is going to be pointed in all kinds of random directions, such that if you were to add them up, they would all cancel out, right? Because they're pointed in random directions and they're just essentially all going to cancel each other out. So when the patient is outside of the MRI scanner, their net magnetization is 0. Okay, so before I go further, I'd like to quickly review vector addition for those of you who are a little rusty on that. So when you're adding a vector, what you want to do is you want to take the tail of the vector you're adding. So this is the tail. This is the tail. Sorry. This is the tail. This is the tip. Okay? So what you want to do is you want to take the tail of the vector you're adding and put it on the tip of the vector you're adding it to. And then you see where you end up. And since we ended up exactly where we started, that means that they add up to 0. So intuitively that should make sense, right? If you have a vector that's pointing to the right of a magnitude m and you have a vector that's pointing to the left, magnitude m, but in the opposite direction, it's going to add up to 0. Fine. So if you have two vectors that are pointed obliquely, right, but they're the same magnitude, the same logic is going to apply. You place the tail on the tip and you end up back where you started, so that's also going to add up to 0. So what about this scenario where you have these 3 vectors that you're adding? So these vectors, right, they're going to cancel, right? Those are going to cancel. But we're going to be left over with this vector. All right, so that the sum of these 3 vectors is just going to be this vector, right? Because these vectors cancel. Okay, so that's basic vector addition. There's one other thing I want to go over. So let's say Well, okay, before we do that, let's define the longitudinal plane and the transverse plane with respect to a patient in an MRI scanner. So let's say that this is the MRI scanner, this is the patient, patient's lying down. So the long axis of the patient, defined, by their, going from their feet to their head, is going to be called the longitudinal plane, or the Z axis, okay? Z axis, let's just call it the axis for now. Whereas the axis that's perpendicular to that is called the transverse axis, or the Y axis. So if we're going to define two vectors, let's say we have a vector that is pointed in the the longitudinal plane, and let's say it has a magnitude of mz, okay? And then we have another vector that has a magnitude my that's totally in the transverse plane. What are they going to add up to? So we do the same thing. You take the, let's do this. So you take the tail of one vector and you put it on the tip of the other one, and then you just draw a line from wherever you started to where you end up. So what you're going to end up with is this vector. So in other words, you can take any oblique vector and you can decompose it into longitudinal and transverse components. So you're going to see this is going to become important in the world of MRI physics, okay? So just a quick primer on vectors. All right, so back to the patient. So their hydrogen nuclei, represented as vectors, are in random orientations when they're outside of the MRI scanner. So if you were to add them all up, essentially they all cancel, right? So my question is, I'm just going to try to undo all these things. Is that going to work? Yes. So my question is, what's going to happen when we move the patient into the MRI scanner? So we're going to move the patient into the MRI scanner. So I'm now going to introduce you to the first component of the MRI scanner, which is called B0, or the static magnetic field. So this is the component of the MRI scanner that's always on. And just to give you some context, you can lift a car with a 1 Tesla magnet. So if you have a 1.5 Tesla MRI scanner, you could easily lift a car with that. So it's a very powerful magnet. So obviously these hydrogen nuclei, functioning as tiny little bar magnets, they're going to interact with the very powerful magnet that's inside the MRI scanner. So let's consider the behavior of bar magnets before we do that. So if you have two bar magnets and you bring them close to each other, what's going to happen? Well, what's going to happen is that they're going to line up essentially anti-parallel to each other, right? So if you're to draw a vector, right, so towards the North Pole, so this one would point to the left and this one would point to the right. So that's what happens when you put two magnets close to each other. So they're going to line up essentially in the same plane but anti-parallel to each other. So something similar is going to happen in the context of MRI. So the hydrogen nuclei are going to line up, some are going to line up parallel, and some are going to line up anti-parallel, such that for every 10,000 hydrogen nuclei, you're going to have 5,003 that are going to line up parallel, and you're going to have 4,997 that are going to line up anti-parallel. So 6 out of 10,000 hydrogen nuclei are going to line up parallel to B0. So as a result, they're not going to cancel. So most of them are going to cancel. These 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 are going to cancel. But those 6 out of 10,000, which I'm just diagramming as 2 here, for every 6 out of 10,000, those are going to add up to something parallel to B0. And that is going to form our net magnetization vector. All right, so now we can clean this up. We don't have to worry about all of these individual guys. Well, all right. Well, we'll leave it for now. It's kind of messy. Let's get rid of them. Okay, so that's going to add up to our net magnetization vector, which I just drew out. Fine. So if we're going to try to detect this net magnetization vector in the longitudinal plane, so it should be pointed exactly in the longitudinal plane. I didn't draw it perfectly, but I think you get the idea. So what are we going to measure? So we're going to measure M, but we're also going to measure B naught, right? We're going to measure any magnetic field that's in that plane. And B naught is millions of times stronger than M. So if we were to try to measure M, essentially all we're going to measure is B naught. It's going to overwhelm M. So that's not going to work. So we have to do something else. So what we do is we use something called a radio frequency coil. And we'll talk about this in part 2, but essentially whenever you have this radio frequency coil component of the MRI machine on, the net magnetization vector, it's going to let me do this? Yes. The net magnetization vector is going to rotate. So let's turn the radio frequency coil on so that we rotate the net magnetization vector 90 degrees to the patient. So it's entirely in the transverse plane. Now let's try to measure it. So if we measure it in the transverse plane, we're only going to detect magnetization that's pointing perpendicular to the patient in the transverse plane. What are we going to measure? So we're going to measure M, right? Because that's pointing perpendicular. But what about B0? We're not going to measure any component of B0, right? Because B0 is entirely oriented in the longitudinal plane. So we have successfully separated M, the magnetism inside the patient, from B0, which is what we use to essentially create the net magnetization vector in the first place. So where does MRI signal come from? It comes from hydrogen nuclei, which in the human body is mainly found in water and fat, but they're oriented in random directions when the patient's outside of the MRI scanner. So we have to bring them into the scanner so that 6 out of every 10,000 are pointing parallel to B0. But we can't detect it yet, right? Because B0 is millions of times stronger than M. So we have to rotate it so that a component of it is 90 degrees to the patient with the radio frequency coil, and that's where MRI signal come from. It's a combination of B0 to generate the net magnetization vector, and then turning on the radio frequency coil so that we can flip it 90 degrees and detect it. So if we go back to our question, MRI measures magnetization inside a patient perpendicular to the static magnetic field, right? Because otherwise, if we tried to measure it in the same axis, in the longitudinal plane, it would just get overwhelmed by it.